This demonstration is intended to illustrate culvert performance. I'm Phil Thompson, representing the Demonstration Projects Division of the Federal Highway Administration. I'm going to demonstrate various inlet types by utilizing this portable hydraulic flume. The relative efficiencies of the various inlets can be judged by the changes in head water, since the discharge will be kept constant. We will start with two plastic culvert models. One represents a smooth pipe and the other a rough pipe. These models are the same length and have the same inside diameter. Throughout this demonstration, we'll be comparing the energy necessary for culvert operation by relating headwater elevations. We'll do this by using the headwater indicator. There are two types of culvert flow, inlet and outlet control. Let's look at outlet control first. There are several factors that influence headwater elevation and outlet control: entrance type, barrel roughness, and tailwater elevation. Let's turn on the flume and look at barrel roughness first. The flume is set on a 0% slope. That is, with the culverts flat. Water is flowing through the rough pipe and the headwater pool has reached equilibrium. Let's mark it and allow the water to flow through the smooth pipe and see what happens to the headwater elevation. As you might expect, the headwater elevation drops. This illustrates that to accommodate the same discharge, a smooth pipe requires less energy than a rough pipe. Another factor that influences culvert design is tailwater elevation. When the culvert is operating with low tailwater, the flow is plunging through critical depth near the outlet. Therefore, critical depth is controlling the outlet velocity, and the headwater pool reflects only those factors upstream from the outlet. As the tailwater elevation is raised, the headwater pool elevation remains constant as long as critical depth controls. However, there is a point where the tailwater drowns out critical depth. Above this point, the headwater and tailwater rise at the same rate. If we hold the tailwater elevation constant above the top of the culvert, you can see the difference in elevation between the headwater and tailwater pools. This elevation difference represents the sum of the losses in the culvert system. Therefore, tailwater depth is an important factor to consider when designing culverts and outlet control. Next, let's look at the factors that influence headwater elevation for inlet control. In inlet control, free surface flow exists throughout the culvert barrel. To show inlet control in the model, we will tilt the flume to increase the culvert slope. Notice that the tilt axis is near the outlet invert. If you watch the headwater, you will see that it remains at the same level as the flume is tilted. The barrel is still flowing full in outlet control. Eventually, a slope is reached where inlet control begins and the barrel operates with free surface flow. When this occurs, the headwater elevation begins to rise. In the field, inlet control occurs at about a 1% slope for a smooth barrel culvert. Let's mark the headwater elevation and switch to the rough barrel. As you can see, the type of barrel doesn't make any difference because the control section is now at the inlet. Next, let's look at different entrance conditions. Several entrance types will be compared to the thin edge projecting entrance. The thin edge projecting entrance represents a metal pipe projecting from the embankment into the pool. This configuration has the greatest entrance loss of any type of culvert pipe installation. With the aid of some dye, you can see the streamlines approaching the intake. This is because of the severe contraction and separation of the flow at the entrance. The water has to make about a 180-degree turn, and as it does, it breaks away from the leading edge and contracts. The contraction is very severe, and only a portion of the barrel area is being utilized. Let's look at several different entrance types and see if we can reduce the severity of the contraction. First, let's mark the headwater for this entrance and use it as a reference. As I try different inlets, this contraction will be reduced. Marking the headwater pool elevation for the thin edge projecting inlet, let's see the improvement that results when an inlet mitered to the fill slope is used. The area of the mitered entrance is larger than the thin edge projecting. Therefore, you would expect a lower headwater elevation. The headwater hasn't changed very much, indicating that the effective flow area is about the same. There is not much improvement with the mitered inlet, and it requires a head wall for structural strength. The next inlet is a pipe with a thick wall. The streamlines entering this inlet do not have to make as severe a turn as the thin edge projecting entrance. The headwater pool level has decreased. When a head wall is added to a concrete or metal pipe, their performance is comparable to that of the thick wall entrance. The headwater pool elevation remains at the same level as for the thick wall pipe. The next improvement is a concrete pipe with a bell end. The headwater pool elevation for the thin wall projecting is here, and for the bell mouth entrance is here. The difference is about 1 pipe diameter. Placing the bell mouth entrance in a head wall will not improve performance. The headwater elevation is about the same as for the bell mouth projecting entrance. This same amount of improvement can be accomplished for a metal pipe by using a bevel. Bevels do not have to be very large. For this 3-inch diameter culvert, the bevel is about 1/8 of an inch. Let's see how it performs. The headwater level is about the same as for the bell end concrete pipe. All of the inlets that we have looked at so far have improved culvert performance. The beveled inlet, however, is termed an improved inlet. There are 2 other improved inlets that we'd like to look at: the side-tapered and slope-tapered inlet. Since the barrel is the most expensive part of the culvert, stroke control should govern the design. The side-tapered entrance has 2 possible control sections, one at the face, one at the throat. Therefore, the face is designed so that it cannot control at the design discharge. Let's see how it operates. The barrel flows almost full. The performance of the culvert has improved so much that the headwater pool elevation has dropped to where the barrel is operating in what is referred to as slug flow. Slug flow is the transition zone between inlet and outlet control. Comparing this headwater elevation with that for the thin edge projecting inlet, you can see that the headwater has dropped from here to here. This drop amounts to 1 1/2 pipe diameters. By using the side tapered inlet, the contraction at the entrance of the culvert has been minimized. Another method of increasing performance is to lower the control section of the culvert. This means placing the throat section below the stream bed. This is accomplished by using a slope-tapered inlet. The outlets and inlets of the two culverts are at the same elevation, but the throat for the slope-tapered entrance is 1 inch lower than the throat of the side-tapered entrance. The difference in the headwater pool levels also is about 1 inch, with the slope-tapered inlet having the lower headwater. The 1 inch represents the amount of fall at the entrance of this slope-tapered culvert. If the fall had been 2 inches, then the headwater pool difference would be 2 inches. So far, just circular culverts have been demonstrated, but the same amount of improvement can be shown for box culverts with improved inlets. To demonstrate this, we'll compare two inlets. One is a box culvert with square edges at the inlet. The other is a slope-tapered inlet similar to those shown previously. This inlet has 1 inch of fall in the sloping section of the entrance. Let's mark the headwater level for the square edge inlet and switch to the slope-tapered inlet. Note the drop in headwater elevation. The drop is about 3 inches in the model, or about 1 pipe diameter. This is comparable to the drop observed in the circular pipe demonstration. The bevel and side tapered entrances for a box culvert also improves culvert performance. The improvement is similar to that shown for circular culverts. Let's summarize what we've talked about. The first step is the beveled entrance. The second step or degree of improvement is the side tapered inlet. This inlet has two control sections, the face and the throat. Providing a large enough opening at the face makes the throat the controlling section. This is desirable in order to utilize as much of the barrel area as possible. The side tapered inlet reduces the culvert entrance contraction to a minimum. The only additional refinement that can be made is to depress the control section below the stream bed. This is accomplished by using the slope-tapered inlet. Lowering the control section provides more head above the control and increased culvert performance. For example, a 6x6 box culvert with a square-edged inlet requires a headwater of 12.5 feet to convey a discharge of 500 CFS. The slope-tapered entrance requires only 7.6 feet of headwater, which is 39.2% reduction compared to the square-edged inlet. Another way to look at this is to hold the headwater constant as you normally would in design and look at the capacity of the culvert. Using 8 feet as the headwater, the capacity can be increased from 336 CFS for a square-edged inlet to 523 CFS for the slope-tapered inlet. This is an increase of more than 55% in the capacity of the culvert by using the improved slope-tapered inlet. In terms of a simple design problem, assume you have a design discharge of 1,000 CFS and allowable headwater of 10 feet. This shows the reduced area necessary to carry the flow by making progressive improvements on the inlet. Since the barrel is the most expensive item, you can realize a cost savings by reducing the barrel size. For example, in North Carolina, a box culvert was reduced from an 8x5 to a 5x4 by adding a slope-tapered inlet. Near Bryson City, North Carolina, a savings of 54% was made on the construction cost of one culvert. A savings of $482,000 has been realized on a culvert near Knoxville, Tennessee. If a conventional box culvert had been used, 3 barrels, each 13 by 14, would have been required. But by using a side-tapered inlet, the culvert was reduced to a double 12 by 12 box. These are but 3 examples taken from a field survey of some 66 installations sent to us by state highway departments. In that field survey, we found a total benefit of $2 million. The range of savings was from $500 on up to $482,000. Since the potential for savings is so great, improved inlets should be investigated for all culverts and inlet control.